Okay, so I'm going to show you some things about 4.3, how derivatives affect the shape of a graph. These are some of the objectives that I'm going to be showing you. Okay, first thing is the derivative tells you whether a function is increasing or decreasing. So if you find out on a particular interval that the first derivative is greater than 0, then we know that that tells you how the function is changing. So if the rate of change is positive, then we know that the function is actually going up. And that makes sense. If we look at from A to B, we notice that the function is increasing, and we also know that the slope of the tangent line the whole time is positive. So that would always be the case whenever it's going up. And then it also makes sense that whenever a function is decreasing, that the derivative would be negative for that whole interval, and so we can see the slope of the tangent line would be also negative there. So first derivative tells you whether the function itself is increasing or decreasing. Okay, the biggest test of this whole section is the first derivative test. So we're going to use the critical numbers, and that's going to help us figure out the local max and the local min. So what we're going to do, you want to jot down the first derivative test for sure. What we're going to say is that if the first derivative changes from negative to positive at that critical number, then we know for a fact that there will be a local minimum at that particular spot. If the first derivative changes from positive to negative at that particular spot, then we know we have a local maximum there. And if we notice that at that critical number that the first derivative, let's say right there, so if the first derivative doesn't change the sign, then there's no local max or min. So I want to give you kind of a graphical picture of this so that you can remember it. So it really makes sense when you look at your normal function there, and you were to find out that the slope of the tangent line changes from positive. Notice the slopes of the tangent lines would be positive right here. Then all of a sudden it would level out. So at this spot, that's the critical number. That's where the first derivative equals 0. So this is your C. And we notice that all of a sudden it goes from positive to negative. So that would tell you that at that spot there would have to be a local max there. So this one is a picture of local max, and we can see the sign change for local max. It goes from positive to negative, and you can see the slopes going from positive to negative. Now when you look at this one, this is where the critical number is, and so if you see the sign changes, the first derivative will go from negative to positive, and whenever it goes from negative to positive, that means that we have a local minimum at that spot. Okay? It is possible to have a critical number where the first derivative, so the slope of the tangent line here, does equal 0, but there isn't a sign change because we have the first derivative is positive the whole time, and then it's still positive, so we don't have a sign change, so there's not a local max or min at that particular critical number. Okay? So this is the most important test, the first derivative test. Okay, let's try an example. So here's a function, and we're going to try to see if we can figure out when it's increasing, when it's decreasing, and then also find the local max and min values. So first thing we do is we go ahead and find the derivative. So f prime of x equals 12x cubed minus 12x squared minus 24x. Then we notice we could take out an x, because they have an x in common. So we take out an x, so that would be 12x squared minus 12x, and then minus 24. You know what? I should have taken out something a little bigger. So let me back up for 1 second. Let me take out something a little bit bigger. So we actually could take out 12x, right? So take out a 12x, it'll be x squared minus x, and then minus 2. That'll be a lot better. So then we're going to set your first derivative equal to 0. Remember, that's how we find our critical numbers. So we set that equal to 0. Make sure everything's factored. So x minus 2 times x plus 1. And you can tell your critical numbers are 0, 2, and negative 1. So we can make a nice sign chart with those numbers. So we have negative 1, we have 0, and then we have 2. So that'll set up the intervals. And then we'll put our factors off to the left. So we have 12x here, we got x minus 2 here, x plus 1, see ya, and then the result. So we're going to try some test points. So to the left of negative 1, let's try to plug in maybe negative 2. So we see that it would be negative here, it would be negative here, it would be negative here. So the result would be negative. Try a little number like negative 0.5 here. So that would be negative, that would be negative, that would be positive. So the result would be positive. Then we could try a test point of 1. So that would be positive, negative, that would be positive, and so the result would be negative, multiplying, positive, negative, positive. Then we could try a test point like 3, so that would be positive, 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 so the result would be positive. Now what we're going to do is we're going to evaluate this sign chart. So we notice that this is the first derivative, remember. So the first derivative goes from negative to positive. That's a sign change. So it goes from negative to positive. Again, that's kind of like this, where it goes from negative to positive. That means there has to be a low point right there. So that's a min. So we would say we have a minimum. We have a minimum at x equals, and it's right there at negative 1. And then it looks like there's another sign change from negative to positive. So that's another minimum. So we have a minimum at x equals negative 1 and x equals, it looks like 2. So we have a minimum at both of those spots. Then you notice that we have a sign change we go from positive to negative right here. And that's a graph kind of like it goes from positive to negative. So there has to be a high point there. So positive to negative, that means that we have a maximum, a local maximum there. So we have a maximum at, and then we would say at x equals, and it looks like at 0. So it's at this spot. So these are where you have them. They aren't the actual values. So if you ever see the word values, you actually need the y coordinates. So we would have to take those numbers and plug them into the original to find out what they are. So what we'd have to do is we'd have to say officially, I'm going to do this. I'm going to say local min at, I'll say local min, let's see, local min at or of, let's see, local min of, and I'm going to say f of negative 1 equals something, and f of 2 equals something. So I took those and I plugged them in. So I plugged in negative 1, I got 0. I plugged in 2, I got negative 27. I'm going to change that color. I plugged in, I got negative 27. And then I have a local max of, and then I could say f of 0 equals 5. So I plugged in 0, and you can tell I've got 5 there. Okay? So these are the answers. Now, the increasing and decreasing, we have to tell the intervals where this function is increasing and decreasing. So it's increasing, what would you say? Let's say, so it's increasing on wherever the first derivative is positive. So on, let's say, negative infinity to, let's say negative 1 to 0. So negative 1 to 0 unioned with, it looks like 2 to infinity. Would you agree? So 2 to infinity. So those two intervals. And then we'd say decreasing on, and that would be wherever the first derivative is negative. Because, again, first derivative determines how the function is changing. So we'd say negative infinity to negative 1, and we would union that with 0 to 2. All right? So there's that one. What about the second derivative? What does the second derivative say about the graph? Well, the second derivative tells you the concavity. So if the second derivative is positive, then that means it's concave up all the time. And then if on a particular interval the second derivative is less than 0 or negative, then it's concave down. Concave up just means that it kind of looks like this, and concave down is kind of what you'd think, that it kind of goes down a little bit like that. So concave up basically means that the rate of change of the first derivative is positive. So the first derivative is changing in a positive fashion. So it's actually increasing. Okay. So we have what's called the second derivative test, and this one's used quite a bit as well. And it helps us find out the local maximums and the local minimums as well. So what you would do there is that you would find the second derivative of a function. And I'll have to do an example of this. But what it means is if you find out the critical number, so let's say you have your critical number, and you plug it into the second derivative, and you find out that your critical number, when you plugged it in, was positive, then that means there has to be a local minimum at that spot. And then the second part of it is that if you plugged in your critical number and you found out that when you plugged in your critical number you got a negative answer, then that means that it's a local maximum. So graphically, the way to explain this, it goes like this. If you knew at a certain spot that you definitely have a first derivative that equals 0, so let's say this spot right here, you knew that this is where the first derivative equals 0, and you plugged that particular value into the second derivative to see whether it was concave up or down, and you plugged it in and you found out, wow, on that particular interval I got a positive answer. Well, if it was a positive answer, then that means it's concave up, and that means at that particular spot you must have found the low spot. That must have been, if it's concave up and that's where the first derivative equals 0, it makes sense that that has to be the minimum. So that's going to make, visually that would make sense that if the first derivative equals 0 and you know that you're concave up on that particular interval or in that spot, then that has to be the low spot. And then if you know for number 2, you know that, so that would go with this graph. Then for this one, if the first derivative equals 0 and you find out that it's concave down on that particular interval, so in other words you plug in the c and you find out it's less than 0, which means it's concave down, then that means that at that spot you must have found the high point, so then there would be a max at that particular spot. So this is kind of an alternative, the second derivative test, to the first derivative test. You wouldn't have to do a full-on sign chart. And this is a really good test. As long as the second derivative is really easy to find, then you could do the second derivative test. It doesn't always work. The first derivative test is more useful, more powerful, more robust, all those things. Okay. All right, let me try at least one more. Actually, let me back up and do that same problem as before, but use the second derivative test. Okay. So let's say I found, let me just rewrite it. So this is that same example. So here's my original function again. Let's see. My original function, go back, is 3x to the 4th minus 4x cubed minus 12x squared plus 5. And then we figured out our first derivative. We got 12x cubed minus 12x squared minus 24x. So then it's not too hard to find the second derivative, so I'm going to go ahead and find that. So second derivative for this one is 36x squared minus 24x and then minus 24. So what we do is we find, so I'm going to use this, second derivative, and I'm going to use the critical numbers that I found before. Remember the critical numbers is where the first derivative equals 0. So the critical numbers that we found before, critical numbers are, from our last problem, were, critical numbers are -1, 0, and 2. So all I would have to do for the second derivative test is I would have to plug in each of those numbers into the second derivative, and I would see whether those numbers are positive or whether they're negative, and that would determine whether they were local max or mins. So I take the f double prime of negative 1 and I plug it in, and I got 36 plus 24, and then I got minus 24. And then that equals 36, which is positive. So that means that it's concave up there. And I found out that that's where the first derivative equals 0. So that means that there has to be a minimum. So there's a minimum at negative 1, like we discovered before. And then for the second derivative of 0, we plug in 0 everywhere. So we'd have 0 minus 0, and then minus 24. So we'd have minus 24. Of course, that's negative. So that tells you it's concave down on that interval, and you found out where the first derivative equals 0. So you must have found a max. So it's true that there's a max at 0, like we found out before. Then if you plug in a 2 into the second derivative, then it would be, it's also positive. So let's say I just plug it in. I know for a fact it's going to be positive. So if that's positive, then again, it's concave up. So that means if I found a spot where the first derivative equals 0, then I found a minimum. And so same thing we found before. We found a minimum at negative 1 and 2. We found a max at 0. All right? Okay. Next thing is just, I want to talk about just what an inflection point is. An inflection point. Inflection point is where the graph changes concavity. So where the graph changes concavity. So that means it's going to change, like graphically. Let me just show you. You know, if you had a graph that was maybe going like this and then like that, this is this whole part here would be concave down. So the blue, this would be concave down. And then there is a spot where it changes concavity. It's probably like right here. It starts, then it's concave up. Right where that changes from concave up, so I'm going to say the red is concave up. Where it changes concavity is called the inflection point. And how that's going to show up analytically is that's going to be where the second derivative changes sign. Okay? So that's going to require us to find the second derivative and then also find the spots where the second derivative equals 0 and then look for a sign change. So let me see if I can do an example where we can actually look for concave up, concave down, etc. Actually, you know what? I think I'll probably stop there and call it good for this part. We'll call this 4.3 part 1, and then I think I'll add a little bit after. Hold on one sec. Let me just see if I'm ambitious enough to do a quick example to figure this out. Let's see. I'm hearing a lot of noise, so I think I'm going to wait. All right.